Hello, Roshan. Audible? Sabish?
Audible, sir. Audible, sir.
Okay.
Yes, sir, you're audible.
Right.
Back. Mechanical science plug. IIT photo வச்சிருக்காரு.
எல்லாம் ஒரு இன்ஸ்பிரேஷன் தான் உங்ககிட்ட இருந்து.
Roshan, have you noticed the Sadish background?
So Satish sir के पीछे में that mechanical department IIT.
Have you noticed it?
Yes sir. Romeo sir.
Excellent.
रोशन जी नमस्कार.
नमस्ते सर, काफी हैंडसम दिख रहे हैं आप.
थैंक यू सो मच. इसीलिए आपने नमस्ते बोला ना. जगन जी बड़े शांत है आज.
मैं हमेशा शांत ही रहता हूँ.
वो एक्चुअली ही इज अ वेरी क्लेवर गाय. ही नोज व्हेन टू स्पीक, हाउ टू स्पीक एंड वेयर टू स्पीक एक्चुअली.
What to speak as well.
बहुत ही गुरुजी.
Hello, good evening to all of you.
Good evening sir.
नमस्ते सर. गुड इवनिंग सर.
Good evening sir.
Good evening, sir. Am I audible?
यस सर.
Yes sir.
Okay, thank you. Is my screen visible to you?
Yes sir.
Yes sir.
Okay. Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes sir.
Anand Kumar, Anand Kumar, Arnachalam,
Sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Rausan Kumar,
Present, sir.
Sabish Kumar,
Yes, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Sir, Vignesh joined, but he's going to miss some mic issues, sir.
I see here.
Yes, sir, he's joined actually.
Okay.
Yeah.
Vijay Raj,
Present, sir.
Vikas,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj,
Present, sir.
Sir, Anand Kumar joined, sir.
okay.
Sorry.
Okay, welcome back. We are in the last topic of chapter 1. Chapter 1 is devoted to understand more about the fuels that we use in IC engine, gasoline and spark ignited engine, and diesel and compression ignited engine. So the major focus of this chapter is,
Hello, sir.
yes,
Sir, Vigneshwaran just had some issue. Present, sir, actually.
okay, I have marked attendance.
Okay, thank you, sir.
Okay. Please mute your mic. Okay, thank you. So the major focus of this chapter is to understand the molecular composition and molecular structure of hydrocarbons present in gasoline and diesel. We have discussed that so far. Now we are in the last topic. We are discussing some of the important properties of gasoline and diesel, which has significant effect on SI and CI engine characteristic. We have also seen that similar to emission legal limit, there are legal limits for fuel quality standard. Okay, so currently we are in BS6 emission now. So we use BS6 fuel, gasoline and diesel in our IC engine. We have so far discussed about these important properties on SI engine characteristic and these properties in CI engine characteristic. Two more important properties that we need to know. One is octane number, which is a measure of antenna quality, and it significantly affects spark ignited engine combustion. Then we have cetane number, which is a measure of ignition quality, and this affects CI engine combustion characteristic. Today we are going to discuss about this octane and cetane number with a focus on how these numbers are measured, what kind of test facilities are used to measure this number. This is important to know because octane number is a fundamental fuel property for SI engine application. You could see here that there are some minimum number, octane number that needs to be achieved in order to use gasoline in SI engine. This RON is research octane number. There are two numbers here. One is research octane number. Second one is motor octane number. I will talk more about this in the next slide. So we have these two numbers, and these are the legal limits. Research octane number should be a minimum value of 91 for gasoline, and motor octane number should be a minimum value of 81 for SI engine application. It can be higher than that. So it is specified that this is a minimum value. It can be higher than these values, but it cannot be lower than this value. That is what it means. So the fuel legally sold in the market should comply with this. And it is a measure of antenna quality. Similarly, cetane number is a measure of ignition quality. A minimum cetane number of 51 is required for all the fuel legally sold in the market. The fuel that we get from the pumping station should have a minimum cetane number value of 51. Please note again, this number can be, cetane number can be higher than 51, but it cannot be lower than 51 according to the legal fuel specification standards. Okay. Then we are going to discuss about this volatility, which has significant effect on SI engine characteristic, and in CI engine it has minimal effect. It affects only particulate formation. So in this class, we are going to discuss about this octane number, cetane number, and volatility characteristic for gasoline and diesel. So coming back to octane number, so this gasoline fuel antenna quality is defined in terms of this measurable property. Octane number is a measurable property. Antenna quality is a qualitative term. Okay, so in order to quantify it, we have introduced this number, which is measurable octane number. One is research octane number. Second one is motor octane number. In India, we take an average of these two, which is specified as anti-knock index. So we take average of research and motor octane number and consider that as anti-knock index, okay, which is a measure of anti-knock quality of gasoline. We already discussed about the effect of hydrocarbon molecular structure on ignition quality. We know normal paraffin is having higher or better ignition quality among all other hydrocarbon classes. Aromatics have very poor ignition quality among all other hydrocarbon classes. This is what we have seen here in terms of cetane number, which is a measure of ignition quality. Normal paraffin is having highest cetane number, which is having better ignition quality. Aromatics have very poor ignition quality, defined with a very low 0 cetane value. The other hydrocarbon classes come in between. I already told you that the cetane and the cetane number and octane number are inversely proportional. In other words, ignition quality and anti-knock quality are inversely proportional. So when I say that ignition quality is better, defined by high cetane number, anti-knock quality will be poor, defined by very low octane number. Very low octane number. Did you understand what I am saying? Cetane number is a measure of ignition quality, meaning how quickly, from the combustion perspective, this is a measure of how quickly an hydrocarbon form radical. Okay, so you know combustion will get started once the radicals are formed. Otherwise, unless the radicals are formed, the combustion even did not get initiated, right? This is what we discussed earlier. So when hydrocarbon readily forms a radical, quickly form radical, we can say that it is having better ignition quality defined by high cetane number value. But anti-knock is a totally different requirement. In a spark ignited engine, the fuel should resist ignition. It should not form radical. Any self-ignition of fuel or mixture will result in knocking combustion. So the fuel should resist ignition. This is what I mean by anti-knock quality. So we see here that these two are inversely proportional or opposite requirement. Okay. Now with that background information, let us come back here. So this is how the cetane number increases. Okay, normal paraffin is having highest cetane number as we have just now seen, and aromatics are having lowest cetane number. You have other classes, olefin, cycloparaffin, and isoparaffin. Now when you look at how the octane number varies, you could see that it is just a reverse of what we have seen here for cetane number. Whatever we have seen and discussed for cetane number, octane number is just reverse. Aromatics are having highest octane number, followed by isoparaffin, cycloparaffin, olefin, and normal paraffin. Normal paraffin will have a very low octane number, meaning that for gasoline composition, we should restrict normal paraffin content, we should increase aromatic content. Okay, so if you look at the fuel specifications, you could see that we are using aromatics up to 35% volume. You need to have such a high proportion of aromatic content, then only we could be able to meet this octane requirement for SI engine. Okay, research octane number of 91 and 81 is very high value. So we will be able to achieve this only if we have a high aromatic content. Okay, so we can use up to 35% aromatic content. I already told you that the refinery processes are more intense to get gasoline with the well-defined specifications as compared to diesel. This is one of the reasons why petrol or gasoline cost is always higher compared to the cost of diesel. So this involves a lot of processing to get an octane number of say 91 and motor octane number of 81. Okay. Now let us look at how this number is measured, how we define this number and how it is measured. So as I have just now said, this anti-knock quality is measured by octane number. We have two numbers, research octane number and motor octane number, RON and MON. This is measured in a special category of engine referred to as a CFR engine. CFR stands for Cooperative Fuel Research Engine. This is a variable compression ratio engine. The measurement conditions are different for RON and MON, as I have presented here. To measure research octane number, engine is run at 600 RPM with an intake temperature of 52 degrees Celsius. To measure motor octane number, engine is run at 900 RPM with an intake temperature of 149 degrees Celsius. You could see that the engine running speed is considerably low compared to the current SI engine vehicle running speed, right? Current SI engines run typically well above 3000 RPM. This is considerably low. One of the reason is this engine is designed in 1930. 1930, you can imagine, it's almost 100 years old. Still we use such an engine to measure and estimate, to measure this octane number, which provides an estimate of antenna quality, because we don't get a replacement. These values are repeatable, reproducible. We don't get a replacement for CFR engine based measurement even today. That's why we still use this. The other important information is this research facility is very expensive. The cost of this engine is around 3 to 5 crores. In IIT Madras, we have something called NCCRD. I'm not sure whether you heard about this. Have you come across this NCCRD?
No, sir.
No, sir.
This NCCRD stands for National Center for Combustion Research and Development. This is first of its kind. Throughout India, only in IIT Madras and IISc Bangalore has this combustion center. So faculty who does research on combustion, including automotive combustion, aerospace combustion, faculty who does research on fuel and combustion are members of this group, combustion research group. Okay, so I'm in the fuel group and automotive engine group, and we are trying to get this engine, CFR engine. It's very expensive, 3 to 5 crore. Only few CFR engines are available here. CPCL and petroleum refineries have this facility. IIP has this facility. Okay, we have only very few CFR engine research facility in India. We are trying to get one for NCCRD. I'm trying to get that. The takeaway for you is this is expensive. The conditions, measurement conditions are different. For RON, it is 600 RPM and 52 degrees Celsius. For MON, it is 900 and 149 degrees Celsius. As I said, this is the old engine design, 1930. That's why the running speed is less compared to the current SI engine, but still we use this. Now, you could see that the temperature, intake temperature is considerably high for motor octane number. This is done to simulate the highway driving condition. We typically run engine under cruise condition, right? Highway, we don't change the speed often. It will be higher speed, and the conditions are severe for knocking. Conditions are severe for knocking because the engine operating temperature will be high. So once you increase intake temperature, what will happen to knocking? Knocking primarily happens due to self-ignition of fuel air mixture. If you increase intake temperature, what will happen to knocking tendency?
It will be prone to knock, sir. Very easily.
It is prone to knock. So we can say that knocking tendency is high in motor octane measurement because we are keeping a very high intake temperature. This is the reason why you see here that this motor octane number value is always lower compared to the research octane number value. This is very low because we provide a severe knocking condition. We are increasing intake temperature up to 149 degrees Celsius. It's a severe knocking condition. That's why its value is low. Okay, so what we do when I say that I'm measuring octane number using CFR engine, we are going to match the antenna quality of gasoline with standard reference fuel. We are going to run the engine with gasoline. We are going to run the engine with standard reference fuel. We are going to match antenna quality of gasoline with reference fuel. Okay, so what we do is the engine will be run with gasoline. It's a variable compression ratio engine, CFR engine. The compression ratio will be varied to get the standard knock intensity. So what will happen when you increase compression ratio of the engine?
Knocking tendency will increase, sir, because
engine is prone to knock because you are increasing in-cylinder pressure and temperature. So self-ignition tendency will increase. This is what I mean by increased knocking tendency. By increasing compression ratio, you are increasing self-ignition tendency. Thereby, we can say that the knocking tendency is high. So in a CFR engine, we will run engine with gasoline initially. The compression ratio will be slowly increased until the engine knocks with a standard knock intensity. We are allowing knocking to happen in this engine, meaning that it's a very robust engine. Okay, that's why its cost is high. We are allowing engine to knock with a standard intensity, knock intensity. Okay, and then we run the engine with the reference fuel. What are the reference fuel we use? The reference fuels are normal heptane. That is one reference fuel. Second one is isooctane. What is this normal heptane class? What is the hydrocarbon class? What is the hydrocarbon class? Normal heptane?
Straight chain polymer, I mean, paraffin.
N-paraffin.
N-paraffin. It's a straight chain. Good. It's normal paraffin, chain-like structure. Just now we have seen that this is having better ignition quality, meaning antenna quality is poor. So this is assigned an octane number of 0 because it's having better ignition quality, very poor antenna quality. It is prone to knock quickly. Second reference fuel is isooctane. What is this class? Isooctane.
It's like
Isoparaffin.
This is isoparaffin class. Isoparaffin is a branched molecular structure. So in the chain, you will have branching. Okay, this is what we have discussed. Because of the branching, the ignition quality is poor. In other words, antenna quality is better. So this is assigned an octane number of 100. So these two reference fuel we are going to use. One is normal heptane, which is a paraffin class with a very poor antenna quality, and isooctane with the isoparaffin class having better antenna quality, assigned an octane number of 100. Okay, so as I said, what we do here when we measure the octane number, engine is run with initially it is run with gasoline. CFR engine is run with gasoline. Compression ratio is varied to get the standard knock intensity. Then the engine is run with reference fuel, which is a mixture of normal heptane and isooctane at the same compression ratio as we have done with gasoline. So you log the compression ratio, then run the engine at the same compression ratio with reference fuel. Right? What we do when we run the engine with reference fuel, we are going to vary the volumetric proportions of normal heptane and isooctane until we get the same knock intensity. So I said that when you run with gasoline, you are allowing the engine to knock with a standard intensity, standard knock intensity. At a particular compression ratio, will reach this. Now you run the engine at the same compression ratio with the reference fuel, normal heptane and isooctane at the same compression ratio. You vary the volumetric proportions of normal heptane and isooctane in such a way that you are getting the same knock intensity. Right? Now, once you get the same knock intensity at the same compression ratio, can I say that the gasoline antenna quality is matched with the antenna quality of reference fuel?
Yes, sir.
Yes. So we are matching the antenna quality of gasoline with reference fuel. Now, at that condition, octane number is defined. Once you do this matching of antenna quality of gasoline with reference fuel, antenna, this octane number is defined as percentage volume of isooctane in that mixture of isooctane and normal heptane, which you know. So this is a known information. From this known information, you are deriving this octane number. Okay, once you match the antenna quality. For example, here I have shown an octane number value of 91 in the specifications. Antenna research octane number of 91. What it says is gasoline with a research octane number of 91. What it means is gasoline has an antenna quality similar to the antenna quality of reference fuel that has 91% by volume of isooctane, 9% by volume of normal heptane. This is what it means. Antenna quality of gasoline with an octane number 91 is similar to antenna quality of reference fuel that consists of 91% isooctane and 9% of normal heptane. Clear? So that is how we measure this octane number. We are basically matching the antenna quality of gasoline with the reference fuel. So similar CFR engine, but CI engine version, CI version, CFR has a SI engine version and CI engine version that will be used to measure the CTA number. Okay, cetane number. So what we do here is we will vary the compression ratio to get the standard ignition delay. Previously, we vary the compression ratio to get the standard knock intensity. Here, we are going to vary compression ratio to get the delay time, standard ignition delay time of 13-degree crank angle. So we will run the engine, CFR engine with diesel, vary the compression ratio until you get the standard ignition delay of 13 degrees. So you know that when you vary the compression ratio, what will happen to delay time? Delay time is going to get varied, right? Ignition delay time is going to get varied, right? We already discussed about this delay time. It's a time between start of fuel injection and start of ignition. That is what is the ignition delay time. Once you vary the compression ratio, what will happen to in-cylinder pressure and temperature?
If it is reduced, it will reduce, it will increase, then increase.
Yeah. So either we can increase in-cylinder pressure and temperature or reduce in-cylinder pressure and temperature. Okay. So in-cylinder pressure and temperature are going to be varied once you vary the compression ratio. After this, when you spray the fuel, say with a higher compression ratio or lower compression ratio, the delay time is going to get varied. This is what we are doing. We are running the CFR engine with diesel. Compression ratio is varied until we get a standard ignition delay time of 13-degree crank angle. Now then we are going to run the engine, CFR engine with reference fuel. Here the reference fuels are different. You could see here that there are two pure hydrocarbons that are used as a reference fuel. One is normal cetane. What is this class? Hydrocarbon class?
And paraffin.
Normal paraffin, chain-like structure, better ignition qualities. It is assigned a cetane number value of 100. Then you have this heptamethylnonane. Heptamethylnonane, what is this class?
It should be, sir, olefin.
N-paraffin. Isoparaffin.
Oh, isoparaffin class. Heptamethyl is hepta is 7. 7 methyl groups are attached to nonane. Okay, so it is having a branched molecular structure, right? 7 methyl groups are attached. So you will have side chains like this. This is having poor ignition quality. It is assigned a cetane number of 15 because of that. This is chain-like structure, better ignition quality, assigned a cetane number of 100. Here you have cetane number 15. So these two pure hydrocarbons will be used as reference fuel. Initially, we run the engine, CFR engine with the diesel until the ignition delay time of 13 is obtained. Basically, we are obtaining this ignition delay time by varying the compression ratio. At the same compression ratio, you are running engine with these two reference fuel. The volumetric proportion of these two fuels will be varied so as to get the same standard ignition delay value of 13 degree. Once you match this ignition delay, we can say that the ignition quality of a given diesel fuel is matched with the ignition quality of this standard reference fuel. This is what we are doing here. Similar to what we have done here to match antenna quality to measure octane number. Here we are matching the ignition quality of diesel with a standard reference fuel to get an estimate of cetane number. Okay. So this is how the cetane number varies with the hydrocarbon molecular structure. We already discussed about this. This is having highest cetane number. This is having lowest cetane number. So we need to include more normal paraffin in the diesel composition. Then only you'll be able to read this minimum cetane number value of 51. So earlier I have discussed about how the US and European diesel fuel cetane number vary because European diesel fuel has a very low aromatic content and very high cetane number. Similarly, aromatic content in American diesel fuel is significantly high, which results in low cetane number value of 40. Okay, for American fuel, diesel fuel. So we need to reduce aromatic content. You could see here that the polyaromatic content is only 8%. In gasoline, it is high, up to 35%. This is reduced in order to increase the cetane number value. So we need to increase normal paraffin content so as to get the better ignition quality, so as to meet the minimum cetane requirement of fuel legal standards. Okay, so that is how we measure this cetane number and octane number for SI and CI engine application. As I said earlier, this measurement facility, CFR engine facility, is very expensive. Because of this, we cannot afford to get this measurement facility. Now, you have an alternate option to get an estimate of ignition quality of diesel. So we have something called C10 index. So basically here we are estimating the ignition quality by using some correlation. One of the correlation I have provided here. Since the measurement facility is very expensive, we can also use this correlation to get an estimate of ignition quality of diesel. So this correlation is proposed by AASTM. I think you know about this AASTM, right? What is AASTM?
Sir, American standards for.
So it is an international standard organization, American Society for Testing and Material. They propose standards for measuring various properties, okay, including CT number. So the CFR engine is expensive. You can use this correlation. This correlation is proposed by ASTM. The number is given here, 4737. That is an ASTM. For each standard, they will provide a reference number. This CCI stands for Calculated C10 Index. Calculated C10 Index. So we are actually calculating ignition quality by using this equation, which is what is this calculated C10 index. When you carefully look at this equation, you have different terms here. One is T10N. T10N is given by this equation. This is based on 10% distillation temperature. I'm going to discuss about distillation temperature in the next topic. Just take a note that you have T10 here, which is based on the measured distillation temperature T10 value. T50 given by this equation. T50 is based on the 50% distillation temperature. T90 is given by this equation. This is based on the 90% distillation temperature. Apart from this, you also have something B. B is also appearing here in the equation, and this B is given by this equation. This equation is used to get B, wherein you have something D. D is density, measured at 15 degrees Celsius. Basically, if you have the measured density value and measured distillation profile value, you will be able to get the ignition quality estimate for diesel using this correlation or applying this correlation. So you can apply this correlation and get an estimate of ignition quality of diesel fuel once you have the measured density value and distillation temperature. Basically, you could observe here that we are deriving ignition quality based on the measured density value and distillation temperature value. Since CFR facility is expensive, the measurement facility for density and distillation temperature are relatively less expensive, right? So based on cost consideration, we can use this correlation, get an estimate of ignition quality from the measured density value and the distillation temperature value. Clear? So we have moved to the last topic, fuel volatility characteristic. This volatility characteristic of gasoline and diesel are provided here. When we discuss about this crude oil refining, one of the process we discuss is fractional distillation, right? Fractional distillation is what we have discussed. And we have discussed that gasoline is a light distillate, meaning it consists of lighter hydrocarbons. Light distillate, what is the temperature range? Boiling range 20 degree to 200 degrees Celsius. That's a boiling range. So it's a mixture of hydrocarbon. You have a range of hydrocarbon with different boiling range. That's why you have been provided with a range rather than a single number. Gasoline comes under light distillate category with a boiling range of 20 degree to 200 degrees Celsius. This is what you are observing here. You can ignore this. This is in degree Fahrenheit on the left side. On the right side, you have temperature in degrees Celsius. You have this profile, distillation profile of gasoline. And what you have on the x-axis is percentage of fuel evaporated, y-axis you have temperature. So we are actually plotting this profile is called distillation profile. So what you do is you take a known or finite volume of gasoline, you add heat to the gasoline, once you add heat to the gasoline, different hydrocarbon will evolve out, distill out at different temperature. Okay, so this plot is obtained based on that. We are tracking the temperature at which the different hydrocarbons distill out from the column. We have taken a known volume of gasoline in a distillation column. We are adding heat. Different hydrocarbon will distill out or evolve at different temperature. The temperature is what we are tracking here and provided in y-axis. Percentage of fuel evaporated is what is provided in the x-axis, and this profile is called distillation profile. So gasoline is a light distillate. As you could see that its boiling temperature starts from around 20 degrees Celsius. It goes all the way up to 200 degrees Celsius. Diesel is classified as heavy distillate. Why it is called heavy distillate? Because it includes heavier hydrocarbon, high molecular weight hydrocarbon. Its boiling range is higher compared to gasoline. It will be 160 degrees Celsius to 380 degrees Celsius. This is a boiling range of gasoline, 160 to 380 degrees Celsius. So you have percentage of fuel evaporated and the associated temperature here in y-axis. It starts around 160 degrees Celsius. It goes all the way up to 380 degrees Celsius. That is a boiling range of diesel. That's why it is categorized as heavy distillate. Okay, so these are measured values. Okay, experimentally measured value using distillation column, and now we are going to see how the volatility or distillation characteristic affect the SI engine and CI engine characteristic. This is a measured data. This gives useful information. Because this temperatures are going to affect the SI engine characteristic. We are going to see now. So the volatility characteristic, fuel volatility. Volatility is a measure of ability of the fuel to vaporize. That is what, in simple terms, this is what is volatility. How quickly the fuel can vaporize. When I say that the fuel is highly volatile, it means it can quickly vaporize. When I say that the fuel is heavy or the fuel is having poor volatility, it means that the fuel cannot vaporize quickly. Diesel is a heavy distillate. It's having poor volatility. Gasoline is a light distillate. It is having better volatility. It can quickly vaporize. So volatility, in the sense, is measurement is the ability of the fuel to vaporize, and this is measured using distillation profile in a column, distillation column, and this is what we have seen. This is a typical profile, distillation profile of gasoline. Here we need to track this three important temperature. One is T10. As marked here, this is a temperature at which 10% of the initial volume of the fuel is vaporized. Temperature at which 10% of initial fuel volume is vaporized. For example, if you take 1 liter of fuel, the temperature at which 100 ml of fuel evaporated is what is the T10 value. The next important temperature we need to track is T50. T50 is the temperature at which 50% of the initial volume, half of initial volume, get evaporated. Okay, that is what is T50. Then we need to track this T90. This is the temperature at which 90% of the initial volume is evaporated. For example, if it is 1 liter, temperature at which 900 ml evaporated, 900 ml volume of fuel evaporated is what is T90 temperature. Okay, so we are tracking temperature at which different volume fractions are distilled out from the column. And these three temperatures, T10, T50 and T90, affect the spark ignited engine characteristics significantly. This is what we are going to see here. T10 affect engine starting characteristic. It also affects evaporative emission. It also affects vapor law characteristic in the engine. Okay, so these are the effects of these three temperatures on the engine, SI engine. Okay, T10, you know, it is an initial boiling range hydrocarbon. This is a mid boiling range hydrocarbon, and this is a final boiling range hydrocarbon, T90. So this initial boiling range hydrocarbon, suppose if the T10 temperature is high, what it means, the gasoline, given gasoline is having poor volatility, this is going to affect the engine starting characteristic. right? It is having significant effect on the starting character. Suppose if you park your vehicle overnight and the next morning, if you park your motorcycle in a cold weather overnight and in the next morning, you have to put a lot of cranking effort, right? Have you noticed it?
Yes, sir. Yes, sir. Many times.
Cranking, yeah. So the effort you need to put for cranking the engine is considerably high when you park your vehicle overnight over a cold weather condition. This is because I already told you that in a spark ignited engine, we introduce fuel under very low pressure, very low temperature condition, meaning we are not providing any external aid for vaporizing the fuel. The fuel has to vaporize by itself. Right at the time of starting, the engine relies heavily on this T10 temperature hydrocarbon. It relies heavily on the low boiling range hydrocarbon. So you have a boiling range from 20 degree to 200 degree. At the time of starting, this low boiling range hydrocarbon has to play a significant role because this hydrocarbon has to quickly vaporize and they should quickly, you know that we are introducing liquid phase fuel. Combustion is a gas phase phenomena. From the liquid phase to gas phase, the fuel should quickly vaporize and also it should mix with the air in a finite proportion. This is what we mean ignitable range. The vaporization has to happen quickly and it has to mix with air within an ignitable range. Once you discharge electric spark, that is how you start the engine, right? At the time of starting the engine, you discharge electric spark. When you discharge electric spark, you need to have ignitable gas phase mixture available in the spark plug location. If you don't have ignitable gas phase hydrocarbon mixture in the spark plug location, whatever cranking effort you do, whatever spark discharge you do, the combustion is not going to start. This is what you are observing when you crank your vehicle, right, in the morning after you park it overnight under cold weather condition, because the vaporization has not happened. Once the vaporization happens, once the fuel stays in the liquid phase, the combustion is not going to start. Okay, so here we have a problem. So what you do normally in the old design engine, what you do normally, you will apply a small lever, right? At the time, right? What is that choke? So you are actually restricting airflow and you are richening the mixture. So what you do by applying that small valve is you are richening the mixture. Generally, you run SI engine under stoichiometric condition. But at the time of starting, the fuel will be supplied more with a given air proportion. Meaning that the fuel will be almost 5 to 10 times richer than the stoichiometric proportion. You are richening the mixture. Why you do that? You are doing that because we want the sufficient low boiling hydrocarbon to get vaporized, and those vaporized hydrocarbon has to mix with oxygen within ignitable range, and that should be available in the spark plug region when you discharge electric spark. Otherwise, the engine is not going to start. So that's why it needs considerable your effort. So what you do finally is you are richening the mixture, you are increasing the fuel volume, thereby you are ensuring that the sufficient low boiling hydrocarbons are vaporized, mixed with the air in the finite proportion, available in the spark plug location, so that once you discharge electric spark, the engine gets started. So the engine starting characteristics are affected by this T10 or low boiling hydrocarbon. If you have a higher T10 temperature, you will have a problem of starting. So we need to keep a track on this T10, ensure that it is somewhat lower so that the engine gets started with ease without any considerable effort. But it cannot be too low also. Suppose if T10 value, temperature value is too low, it means the fuel is highly volatile. High volatility fuel, low boiling hydrocarbon fuel will increase evaporative emissions. What is this evaporative emission? Once you open the gasoline fuel tank or petrol fuel tank, you could feel the smell. I already said about this, right? Because once you open the tank, this low boiling hydrocarbon evolve out from the tank. If you have a T10 value considerably low, what it will do is it will increase the evaporative emission because you have a very high volatility fuel. And once you keep your tank, fuel tank open for some time, you will have a loss of fuel, actually, loss of fuel. This is what I mean by evaporative emission. Hydrocarbons evolve out of the tank and get dissipated in the surrounding ambient air. Okay, this is what is mean by evaporative emission. And please have a note that some of these hydrocarbons are carcinogenic. I already said about this because any hydrocarbon with a benzene ring has the potential to cause cancer. So we need to make sure that we are not inhaling any of these hydrocarbons. Okay, and this is what I mean by evaporative emission. This will be high if T10 temperature is low. So we need to keep a check on that also. Also, the other potential problem is vapor lock. Once the fuel is highly volatile, it will form vapor. It will vaporize in the line itself, fuel line itself. Once the fuel vaporizes, you know there is a considerable difference in density between a vapor phase and liquid phase. This vapor phase, when it is present in the line, fuel line, it is going to obstruct the free flow of fuel, free flow of liquid fuel. This is what I mean by vapor lock problem. So this also will be a potential problem when T10 temperature is too low. Okay, so you have opposite effects. If it is too high, it affects starting. If it is too low, it increases evaporative emission, it causes vapor lock. So you need to keep a check on T10 for the engine design and ensure that you have an optimal T10 value. Then you have this T50. T50 is a mid-boiling range hydrocarbon. This mid-boiling range hydrocarbon primarily affects the warm-up. You know, after the engine gets started, it needs some time to reach warm-up stage. What is warm-up? Engine components are initially at a lower temperature. It takes some time for the component to reach the warm-up. During that warm-up stage, this mid-boiling range hydrocarbon play a considerable role because we need to have sufficient mid-boiling range hydrocarbon with a lower T50 value so that the engine reaches warm-up stage quickly. Otherwise, if it takes more time for vaporization, again the warm-up will take more time and acceleration response will be poor. So what we expect once you press the acceleration pedal, the engine should deliver higher power output immediately. It means the combustion event should proceed quickly and naturally should happen quickly so that the power output is increased. So this is what I mean by better acceleration response. Sometimes the engine will be sluggish. You would have noticed you are pressing the pedal, but the required power is not delivered. One of the reasons is if the mid-boiling range hydrocarbon temperatures are so high, the vaporization event will be delayed. And please always note that combustion is gas phase phenomena. We are introducing liquid phase fuel into the engine. It should get into gas phase as quickly as possible. Okay, so sometimes you will have a sluggish acceleration response. One of the reasons is the fuel is having a high T50 temperature, or in other words, poor volatility characteristic. Then we have this T90. T90 is a end boiling range heavier hydrocarbon present in gasoline. This has two effects. One is fuel economy. How it affects fuel economy? Based on your understanding, can you tell me how this T90 affects fuel economy? Hello?
More the T90, more the thermal efficiency. More the temperature high, more the thermal efficiency. So we'll get.
Yeah. So first of all, when I say that this T90 temperature, when it is higher, it means what kind of hydrocarbons are present in the fuel?
Higher density. Heavier.
Exactly, higher density hydrocarbon. Higher density hydrocarbon will, when you say density is high, it means molar mass or molecular weight is high. Heavier fuel. Okay, heavier fuel will increase density, and that happens with increase in T90 temperature. When I say density is high, we already discussed about this effect of density on fuel economy. When I say density is high, the mass that is burnt in the engine is also high for the given volume that you meter in your injection system. V is constant, M is high if rho is high, rho is density. So high density fuel will increase fuel economy because you are allowing more mass into the engine. More energy release happen. That's why the fuel economy is better, but it cannot be too high. The other problem, negative effect is deposits will be increased. Any heavier fuel will take more time for vaporization. It stays in the liquid phase, and we have discussed that this causes oil dilution. There are two potential problems: oil dilution and CC deposit, combustion chamber deposit. Oil dilution happens because the fuel stays in the liquid phase for a longer time. It dilutes the lubricating oil. By doing this, it increases wear and tear. And also the combustion event will happen with a mixture of lubricating oil and fuel. And that is how you get into more deposits. combustion chamber deposit. You know, low boil is a heavier hydrocarbon, right? It's going to increase the soot or deposit formation in the engine. So once you run the engine after, for a longer period of time, once you open the engine, you could see the carbon deposits, right? This is quite possible, right? You often see the deposits in the combustion chamber, in the piston crown, and so on. After you run the vehicle for a considerable period of time, so deposits start to form primarily with the heavier hydrocarbon present in gasoline. Okay, and this is one of the potential problem. We need to keep a check on T90. It cannot be too low or too high. If it is too low, it's going to reduce the fuel economy. If it is too high, it is going to increase the deposit. So there is a trade-off. So you know, an engine, always there is a trade-off. So you need to, that's why we often use the word optimal proportion. So we need to ensure that the T90 value is optimal so that you don't have any negative effect, okay, in the engine or vehicle system. Now, when you look at distillation effects on the CA engine characteristic, whatever we have discussed so far is applicable for SI engine. This is what is the volatility characteristic for gasoline. This is the diesel volatility characteristic. In a CA engine, T10 or T50 do not have any effect. There is no effect of T10 distillation temperature, if that is initial distillation temperature, as well as T50. Can anyone tell me why?
Because the pressure and temperature conditions are very high in the combustion chamber.
Yes. At the time of spraying the fuel, you spray the fuel at a higher pressure, and you are spraying the fuel during the end of compression stroke in the engine cycle. At that point of time, inside the cylinder, you have high pressure, high temperature air. So you have better external conditions for vaporizing the fuel. You have better external conditions in terms of higher pressure, higher temperature, which will help in quickly vaporizing the fuel. So vaporization is not a problem, severe problem in CI engine. However, it is a severe problem in SI engine because the fuel has to vaporize by itself since the pressure and temperature at the time of introducing fuel are very low. Here it is very high. So T10 or T50 temperature do not have any role to play in a CI engine characteristic. However, T90, which is a end boiling range hydrocarbon, that will affect diesel engine characteristic. You could see here that T95 is regulated in the specification standard. It should not be higher than 360, which is a max value. Otherwise, it leads to particulate formation. You will have more particulate or soot formation. Particulate is a complex mixture. One of the major component of particulate is soot, solid carbon particle. This particle formation will increase once you have a higher value of T95, okay, end boiling range hydrocarbon, because that means that the fuel you have is having a heavier hydrocarbon. Heavier hydrocarbon are prone to cause deposits. This is the only problem with distillation characteristic, diesel distillation characteristic. Only the high-end boiling range hydrocarbon needs to be checked. Okay, the low and mid boiling range hydrocarbon need not be checked because we have better conditions for fuel vaporization. With this, I conclude this chapter 1. I'll give a brief overview of second chapter content, and I will start this in the next class. So in the second chapter, we are going to discuss about thermodynamics of combustion. The actual combustion event in SI as well as in CA engine is complex because it happens at very high temperature with a very small time scale. It's a combination of high temperature and small time scale. Because of this, we don't have analytical capability to completely resolve what is happening during combustion. Since what I mean here, analytical capability is about the instruments that we have currently. They have their own limitation in capturing the combustion event perfectly because this event is happening at very high temperature, well above 2000 Kelvin, very small time scale, nanosecond or microsecond time scale, depending on the engine running speed. High temperature, very low time scale. So it's very difficult to capture what is happening during this period of time at that higher temperature. This is the complexity of SI and CA engine combustion. That's why before we start discussion on actual combustion event, we are starting with a thermodynamic based approach. You know, thermodynamic approach is based on steady state approximation. We focus on the state of the working fluid before combustion and after combustion. What is happening during combustion is highly transient. So we focus on steady state before combustion and after combustion. We apply the laws of thermodynamics, first law and second law we are going to apply. And by doing this, we are going to get useful information or parameters about the combustion event to analyze the combustion event. The useful information you can get by applying thermodynamic principles are you can derive information about the energy that is released during combustion. We can get information about the maximum flame temperature reached because of the combustion event. We can also get information about the product composition. Some of the products are objectionable pollutant, so we need to have an estimate of the product quantity, combustion product quantity. Those information we can get by applying principles of thermodynamics. So in this chapter, we are going to discuss about what kind of information we can derive by applying thermodynamic principles. And thermodynamics is a steady state approximation. It do not provide any transient information. What is transient information? Transient information is about how much of energy is released with respect to time. This is also referred as rate of energy release and rate at which the pollutant form. These are transient information. You cannot get this transient information by applying thermodynamic principle. That's why I will close this chapter with a brief discussion on chemical kinetics. Chemical kinetics provides transient information about combustion event, meaning we can get an estimate of rate of thermal energy release. We can get an estimate of rate at which the pollutants or products, combustion products are formed by applying chemical kinetic principle. So these are the contents we are going to discuss in chapter 2. I will continue this in the next class. If you have any questions, you can ask now.
Sir, I have a query regarding CFR engine.
Mm-hmm.
So, if anyway we are going to compare with a reference fuel for getting, let's say, for getting an octane number for a gasoline sample, why don't we use any engine where we can simply compare between the knocking tendency of reference fuel versus the sample fuel?
No, the engine is sturdy. CFR engine is sturdy and it's having a different design. You see that the engine running speed is also very low. Okay, so basically any property measurement is done under reproducible conditions. So when I say it's a property measurement is done under controlled and reproducible condition. So we cannot use any other engine to replicate or reproduce a cetane number or octane number data. Point number one. Point number two, we are allowing the engine to knock. It's very sturdy. The engine is sturdy, right? I said that when you do octane measurement, you are allowing the engine to knock with a standard intensity, knock intensity. CFR engine is more reliable from that perspective. One, it gives you reproducible data because it's a property. Second one, you are allowing the engine to knock with a standard intensity.
Right, sir. That answers my question. Thank you, sir.
Thank you.
Sir?
Yes.
Sir, is it any temperature range available for T10, T50 and T90?
Any temperature range other than T10? Other than means what do you mean by other than?
No, representing the T20, T50 and T90.
Okay, so these are representative values which gives a measure of what kind of hydrocarbons are present in gasoline and what are their volatility characteristics. So we are picking initial boiling range hydrocarbon, that is T10, mid boiling range hydrocarbon, that is T50. T90 is almost near the end, right? So it's a end boiling range hydrocarbon. These three are representative values, and this is enough to study the volatility characteristics.
Okay, sir.
Fine.
Sir, am I audible?
Yeah, yes.
Just one practical query. Basis this three different temperatures. It's just based on some customer-based experiences. For example, if I go to the petrol bunk of Indian Oil and if I go to the petrol bunk of Bharat, there are going to be different fuel qualities of gasoline. And what is happening is there are times that my vehicle is starting a bit late and my vehicle is not giving good fuel efficiency, something like that for a particular petrol bunk, and for a particular petrol bunk it is different. So it is based on these three parameters, or I mean it's based on these temperatures only, or majorly based on these temperatures, I mean.
Majorly, yeah, because fuel has a significant role to play in whatever I said, T10, T50 and T90. But I'm surprised that in different pumping stations, you are getting different experience in terms of starting and warm up. That should not be the case because, as I said, any fuel legally sold in the market, irrespective of the pumping station you go on fuel, it should comply with all the standards, fuel specification standard. What I have put in the table is only very few properties. I picked up only important properties and I have highlighted those effects on the engine. Other than this, there is a complete list, which is a long list, and any pumping station which is legally selling fuel should comply with all those standards.
Understood, sir. The term legally is a little bit floating around. So for that sense,
Yeah, it should see. It can be in the range. You could see that most of the properties are not one value, right? It's a range, right? I said minimum is 51. CT number. It can be higher than that, but it cannot be lower than that. That is a legal requirement. And distillation generally is specified in a range with a minimum or maximum value. So between one pumping station to other pumping station, there may be small values in density and other properties. Okay, that's why you always have a range, but it cannot be outside that bound, outside the range. Then that is something that needs to be checked because it's going to damage your vehicle, right? As I said, the purpose of introducing this legal fuel specification is to ensure that the end user is comfortable in using the fuel and it is not damaging the vehicle.
noted, sir. Thank you.
Okay. Okay, fine. Thank you. It's time up. I close here. Yeah, there's someone asked something.
Sir, the reference book for for the next chapter that you are going to teach us is Haywood is a good reference, right, sir?
Which one? What is the book you said?
John B. Haywood.
Haywood is good, and Campbell. Campbell deals with thermodynamic aspects of combustion. It is there in the reference list I have provided.
Okay, sir. Fine.
Fine. So I close here. I'll meet you tomorrow.
Do we have PDF of that book, sir? If available with you?
I don't know. You may have to check. Anyway, it is a copyrighted book, so we need to. So we should not violate the copyright law. That's why I said in my email also. Right?
Yes, sir. We will respect that, sir. We will never violate the rules set by you, sir.
Okay, fine. Thank you.
Thank
I
you, sir.
stop here. I will see you tomorrow at 6 o'clock. Thank you. Bye.
Thank you, sir.
Thanks for.
Thank you, sir.
Thank you, sir.